Hi guys! In this video, we are going to practice evaluating expressions in word problems, specifically exponential expressions. So in this video, we will go through 3 different examples. We will write the expression or the function for each example, and then we will evaluate that function for a specific value. So our first example says, the number of bacteria in a petri dish is multiplied by a factor of 1.2 every hour. Initially, there were 500 bacteria. So to be able to write our exponential function, we need to know the initial value, and we need to know the growth or decay factor. In this problem, the initial value is going to be 500 because they tell me initially there were 500 bacteria. I'm using those keywords that tell me what we are starting by, and that's going to be my initial value wherever we start. Then I am asking, is this growth or is this decay? So let's think about the situation of bacteria in a petri dish. Will the number of bacteria in a petri dish grow, or will that number get smaller? Well, the bacteria will grow. And we also have that signal because they use the word multiply. So I know that this is growth. So I know that my factor should be more than 1 because it is growth. So what is the growth or decay factor? Well, they tell me that it is multiplied by a factor of 1.2 every hour. So our growth or decay factor is going to be 1.2. The last question that is really important for a word problem is to know what our variable is. How much are we changing, or what are we changing every time? In this case, we are looking at every hour. So the variable is going to be the number of hours. That is going to be what we are inputting to figure out how much bacteria that we have. So let's write an expression that shows our scenario. And we could even say, we could say that H is the number of hours and B is the number of bacteria. You notice that I'm not using X and Y because I'm using letters that are relevant for the problem that we're solving. So they ask us to write an expression. Well, I know that the number of bacteria, so B is now our output because that's what we're going to be calculating. And remember that an exponential function is expressed, you have y equals a times b to the power of x. So you have your initial value, this is your factor, and then your x and your y. So in this case, b is equal to 500 times 1.2 to the power of h. So I started at 500, my factor is 1.2, and the thing I am inputting is going to be h. So write and evaluate an expression for the number of bacteria after 3 hours. And this is why using h as our variable is going to be helpful, because I now know that they're telling me that h is 3. So I can look for what is 500 times 1.2 to the power of 3. To evaluate this, I can take my calculator. I have to open it up again. And if I take my calculator, so if I take my calculator and turn it on, I can do 500 parentheses 1.2. To do an exponent, I use this little caret button, and I'm going to put an exponent of 3. And that tells us that we will have 864 bacteria after 3 hours. So here I wrote the expression, and I actually evaluated that expression for 3 hours. So let's try another example. The number of nano-related patents that are granted in the US increases by a factor of 1.2 every year. In 1991, there were 60 nano-related patents. So what is the initial value? Well, they don't tell us starting or initially, but they do tell us 1991. So we are actually going to use 1991 as our initial value. We're going to say that we are starting at 1991. So we are starting at 1991. So our initial value will be 60. Now, is this going to be growth or decay? We see that word increases, so we know that it is growth. And because it tells us by a factor of 1.2, our growth factor is going to be 1.2. Now let's look at what our variables are going to be. Our input, we are going to say that y, or let's say time. T is, we're going to use that because it's time. So that'll be the number of years after 1991. Right, so number of years after 1991, 0 would be at 1991, 1 year would be 1 after, which would be 1992, 2 years would be 1993. It's a lot easier if you just take this year and set it equal to 0, right? And then our output, that is going to be n for the number of nano-related patents. So once again, these are those let statements, right? We are defining our variables so that when we write our expression, it makes sense. So let's write an expression. We want n equals, remember that we have y equals a times b to the power of x. So it is going to be 60 times 1.2 to the power of t. I just chose not to use the letter y for years because y is often represented as our output, and I didn't want to make it too confusing. So now let's look at the expression for the number of nano-related patents in 1998. So how many years is 1998? 1998 is 7 years after 1991. So in this case, t is 7. So n is going to be 60 times 1.2 to the power of 7. And if I take my calculator, I could do 60 parentheses 1.2 to the power of 7, 60. And we get 214.99. Now, because this is patents, you can't have half of a patent. So we are going to round that up to 215 patents. So once again, you want to use logic here. If we're talking of number of people, we're not going to consider half of a person. So we are going to always round it to the whole number. Last one. A computer sells for $900 and loses 30% of its value per year. So what is the initial value? Where do you think we started? We started at $900. Now, is this growth or decay? This is going to be decay because we are losing. So we know that in decay, our growth or decay factor should be less than 1. So 30%, think back to what you learned in elementary school, converting percents and decimals. This is going to be 0.3. So if it is losing 30% per year, it's actually 1 minus 0.3 to give us 0.7. It's because it's keeping 70% of its value every year. When we're talking about exponential functions, we're not going to be talking about how much we're losing. We're asking how much we're keeping, actually. So we're keeping 70%. So our growth or decay factor is going to be 0.7. Now our variables, our input, we can say t is going to be the number of years after purchase, and then our output will be v, could be the value. Once again, remember I'm using t for time instead of y for years just because we're used to x and y representing certain things. And let's write our expression. V equals 900 times 0.7 to the power of t. So this means that every year we are going to keep 70% of its value because we lost 30% of its value. So write and evaluate an expression for its value after 5 years. So that means that t is 5. So v equals 900 times 0.7 to the power of 5. And then you can take out your calculator and do 900 times 0.7 to the power of 5. And we will say that it is valued at $151.26. Now in this case, I knew to leave 2 decimal places because we have dollars and cents. And that is some examples for how you can write expressions and functions based on a word problem for exponential functions. Thank you.